What up, people? Today we are going to be talking about 7.3, factored form of a quadratic function. So, as you remember from grade 10, you were able to factor quadratic functions, and at the beginning of this unit, we practiced that factoring to make sure that it was all fresh back in your mind. We will be doing some factoring starting now, really, but this is what factored form of a quadratic function looks like. So, it is when I have my y equal to some GCF. My GCF is represented by that a value. And then I have my factored form here. So, x minus r, which is some number, and x minus s, which is some number. Okay. Each factor can be used to determine the zeros, or my x-intercepts, of the function. Okay. If the function has no zeros, then it cannot be written in factored form. Okay, that's something important to realize. So if the function has no zeros, or no x-intercepts, right? That graph does not touch the x-axis, then, oops, that's kind of messy there. Then it cannot be written in factored form. Alrighty. So, the factored form of a quadratic function can be used to determine different characteristics of the graph. So we could determine x-intercepts, we could determine y-intercepts. The a value is sometimes useful, and we could figure out the axis of symmetry as well. So, just going through these things, quick reminder, when x-intercepts occur, that is always that it occurs when our y value is equal to 0. X-intercepts always occur when y is equal to 0. So, if we want to figure out what our x-intercepts are, well, we can just plug in 0 for y and get the rest of our equation. Right? Because if our equation is y is equal to a times x minus r times x minus s, then if we want to find the x-intercepts and y is equal to 0, we just plug in 0 for y and we can solve for x. Now, if you think back to our review of factoring, at the end of that review, we said solve by factoring. And we noticed that we had a multiplication statement between two or more things. Okay? Here we have a multiplication statement of three things. A, which is some number, being multiplied by x minus r, which is being multiplied by x minus s. And if we have two or more things multiplying to equal to 0, that means at least one of those terms has to be equal to 0. So let's write that down just so that we can remember that. So when two or more terms multiply to 0, then at least one of those terms must equal 0 itself. Right? Because to get a multiplication or get a product to equal to 0, 0 times something will give me 0. We have to have at least one of those zeros exist. So, just like we did before, we look at our values or terms that have the x involved, and we say, well, what if this guy were to equal to 0? Then what? Or what if this guy were to equal to 0? Then what? Notice that we don't say, well, what if a is equal to 0? That's because a represents a number. And that number cannot equal to 0, because otherwise then the whole thing would equal to 0 and we wouldn't have a quadratic function to begin with. So we're only pulling down the values that have x involved in them. Okay? If we want to go ahead and solve for x, well, we can go, well, plus r on either side. And we have x is equal to r. And same thing, plus s on either side. and we have x is equal to s. So when we are looking at factored form of a quadratic function, we can directly say, well, our x-intercepts are that r value and that s value. Those are these guys here. These are my x-intercepts. All right, next off, y-intercepts. And remember that y-intercepts always occur when x is equal to 0. So with that being said, we can go ahead and plug in 0 every single time we see an x. So we have 0 minus r and 0 minus s. Okay, so we take that original factored form of an equation and we plug in a 0 every single time we see an x in order to solve for the y-intercept. And we could simplify this a little bit. So y is equal to a times negative r times negative s. And we have two negatives being multiplied together, right? We have negative r times negative s. So instead we could say two negatives cancel to give me a positive. So a times r times s will give me whatever my y-intercept is. So this is my y-intercept. Alrighty. My a value, that a value. Let's see here. My a value is the GCF of my trinomial. Right, I took out the greatest common factor at the very beginning because before I factor anything, I always want to make sure that I'm pulling out that greatest common factor. So that is what the a value represents. In factored form, just like the original standard form of my quadratic function, the a value denotes the direction of opening. Of my parabola. So, if we have a being a positive number, so the a value is positive, that means the parabola opens up. So it opens like this, which means that it will have a minimum. If we have a be less than 0, that implies that our a value is negative, which means the parabola is going to open downwards. And it's going to look something like that. And if it looks like that, that means that there's going to be a maximum. So our a value, that GCF of our trinomial, can tell us whether the parabola opens up or down, which gives us a hint of whether we have a minimum or a maximum value. The last thing is our axis of symmetry. And we know that all parabolas are symmetric. Parabolas are symmetric. So, kind of a cool thing to think about. Let me draw a picture. I'm going to delete this picture after. Is that if we have a parabola that looks like, I want to draw a nice parabola. That's as nice as I can get here. If we have a parabola that looks like this, we have two x-intercepts. Okay? Because it's symmetric, my axis of symmetry, a little off there. My axis of symmetry that goes through my vertex is right smack dab in the middle. They will be equidistant from both x-intercepts. So to find my axis of symmetry, I can take the average, or that location that is smack dab in between my two x-intercepts, to determine that axis of symmetry. Okay, so let's try and write that down. So the axis of symmetry passes through the vertex that will always be located directly in between both x-intercepts. Directly in between both x-intercepts. So to find the middle of those two x-intercepts, we take the average. All right, so if we know my x-intercepts are R and S, right? We know that from these guys earlier when we determined the x-intercepts. My average is going to be the two of those added together divided by 2, because there's two numbers I'm added together. And I know that sometimes when we're talking about this in like a general context, it's a little bit harder to picture. But I promise you, as we go through and start working on the next two examples that we have left in the notes, that it'll start to make a little bit more sense. Alrighty. So we are going to look at two different graphs. And we're going to look at all of these different characteristics. So the direction of opening, does it have a max or a min? Let's look at the x-intercepts, axis of symmetry, vertex, y-intercepts, domain, range, all that jazz. And we're going to graph it along the way as we go. Once we've successfully graphed it, we're going to use Desmos to confirm that we are able to get the exact same response. Okay? So, for starters, we have this as our equation. And remember that our factored form of our equation follows this. Y is equal to A times x minus r times x minus s. Okay. So our direction of opening is based on our A value. Our A value in this case is just this 1, right? Because we don't write the ones. It's not 0, because if it was 0, the whole thing would equal to 0. But our A value is 1. And because 1 is greater than 0, it's a positive number, we are going to have our direction of opening be up. Okay, so we should get a parabola that opens upwards. Boom. Well, if we're opening this way, are we going to have a maximum or a minimum? Well, we should have a minimum, right? Because this is our minimum value down there. All right, next are our x-intercepts. And remember that for our x-intercepts, our x-intercepts occur when y is equal to 0. Okay, so based on what we did on the previous page, we said that x is equal to r and x is equal to s. In our equation, we are given negative r. So to find whatever positive r is, it's the opposite sign. So here we have x is equal to 3. And here we have x is equal to 5. And if you don't believe me, let me show you a little bit work on the bottom just to confirm here. So we have y is equal to x minus 3 times x minus 5. Remember that x-intercepts occur when y is equal to 0. So if we plug that in, we have 0 is equal to x minus 3 times x minus 5. One of these two things has to be 0. So if x minus 3 is equal to 0, we could add 3 to both sides, and we get x is equal to 3. And if x minus 5 is equal to 0, after adding 5 to both sides, we get x is equal to 5. And that's exactly what we get up here as well. The idea behind factored form and doing what we did on the previous page is so that we don't actually have to do all of the work by hand, which we could, right? We're more than capable of doing that. But that way we can actually go ahead and just look at that equation and understand where that information comes from. That's the benefit of having factored form, is that you could read a lot of the information pretty quickly. All right. The axis of symmetry. So remember that the axis of symmetry occurs right smack dab between the two x-intercepts. So we take the average of those two values. So we go x is equal to 3 plus 5 divided by 2. So that's 8 over 2, which is x is equal to 4. Right, which makes sense. We have our axis of symmetry along this imaginary vertical line at x is equal to 4. Now, we know our axis of symmetry has the same x-coordinate of our vertex, which means our vertex is going to be 4 comma something. To figure out what our vertex is, when we have our equation y is equal to x minus 3 times x minus 5, if we plug in x is equal to 4, we could figure out what this y value is going to be. Okay, so instead of x, we are going to plug in 4. And we are going to solve for y. So y is equal to 4 minus 3 is 1. 4 minus 5 is negative 1. 1 times negative 1 is negative 1. So our vertex here is going to be 4 comma negative 1. Next, our y-intercept. Remembering that our y-intercept occurs when x is equal to 0. On the previous page, we said that y is equal to a times r times s. Right? We know that a is 1, r is 3, s is 5, so y is going to be multiplying all those together, y is 15. And so we could use our factored form to easily get that. Again, if you have a hard time understanding that and you just rather do it in a way that makes a little bit more sense, we know that our y-intercepts occur when x is equal to 0. So if I go and plug in my original formula, or my original equation, and then every single time I see an x, I plug in a 0 instead. 0, 0. Then I end up with y is equal to negative 3 times negative 5, which gives me positive 15. Right, so I get the same thing either way, but the way that we did over here is the advantage of factored form, is that it's a little bit easier to do. You don't have to show all of your work in the same way. Okay. Alrighty. At this point, before we do our domain and our range, we are going to graph this parabola. We're going to do it, and it's going to be great. So the way that we like to graph this is I like to plot all of the points that we know, and then use our axis of symmetry to find any symmetric points, and then continue drawing the line. So a couple points that we know already, or maybe highlight in green. Well, we know the vertex. We know our x-intercepts, and we know our y-intercept. So we're going to go ahead and plot those. So we have our vertex at 4. So 1, 2, 3, 4. 4, negative 1. So I should have the point right there. My x-intercepts occur at 3, and 5. So I have this point here and this point here. And I have a y-intercept occurring at 15. So 2, 4, 6, 8, 10, 12, 14, 15. All right. Before I like connecting anything, I like to draw, I don't know if that's very obvious. Maybe do it in a brighter color. My axis of symmetry here. And again, the axis of symmetry is imaginary, but the reason that I like using it is to notice, what point did I take a shot? That if I have a point on the left-hand side of that axis of symmetry, I should also have a point on the right-hand side. And that usually comes in most handy when I'm looking at my y-intercept here. Right? I have a y-intercept 4 away from my axis of symmetry on the left. So I should have an identical point 4 away to the right. So I'm going to draw a point in here. From this point, all of my other points have symmetric counterpoints. And I'm going to connect the dots using a smooth curve in the best way I can. I'm going to connect the dots, and I'm going to draw arrows at the end of this on either side. Just to confirm that we're on the right page here, I'm going to open Desmos, and I'm going to plug in the same equation. So y is equal to x minus 3 times x minus 5. Okay, and I'm going to look at all these points and notice I've got the same ones, which is super totally awesome. And it won't show me that symmetric point because it's not a key characteristic point, but I could see that I have it at, it looks like 8, 15. So just to confirm, x is equal to 8, I have that same point there as well. So that's always nice. We could use Desmos to double check that we're doing the right things. Lastly, we have to figure out our domain and our range. And our domain and range are easiest to figure out once we've drawn our graph. Okay, so that's why we stopped and drew it first, and then we're figuring out our domain and range afterwards. So our domain is from all the way furthest left to all the way furthest right, which happens to be negative infinity to positive infinity, or in set notation, the set of all x, such that x is an element of the reals. And for our range, we go bottoms up. Our smallest value of y is our -1. -1 is included, so we use those square brackets all the way to positive infinity. And we have the set of all y such that y is greater than or equal to -1, and y is an element of the reals. Alrighty. So we were able to figure out all that information. We didn't actually need Desmos. We used Desmos just to kind of confirm that we were doing the right things. But we didn't even need Desmos. We could figure out all that information from factored form, which is kind of great. We have one more example in factored form. And I want you to pause the video, try it out on your own, because it's following the exact same steps. And then we will reconvene and do it together. So pause the video now. Alright, and welcome back. So we are taking a look at this equation here, and we're going to kind of go through it a little bit more quickly, because hopefully you've done it on your own and you're now just checking your answers. So for starters here, we have our a value as -1/4. And fractions are fine as a values. And -1/4 is actually less than 0, which means we are opening down. And if we are opening down, that means we are going to have a maximum. All right, the next thing we have are our x-intercepts. And remember that our x-intercepts is x is equal to r and x is equal to s. Or you could do it a little bit of the longer way, and that's when y is equal to 0. You could plug in 0 for y and figure it out the same way. But regardless of what you do, you should end up with x is equal to 6 and x is equal to -2. And again, you can express them as coordinate points as well, if that is something that you prefer. Both represent the exact same information. So x is 6 and x is equal to -2. For my axis of symmetry occurs smack dab between my two x-intercepts, so I take the average of those. So I go 6 plus -2 over 2, which is 4 over 2, which means my axis of symmetry occurs at x is equal to 2. My vertex, remember that I take my x-coordinate of my vertex to find my axis of symmetry. So if I have my axis of symmetry, I can say that they have the same x-coordinate of my vertex. So that occurs when x is equal to 2. So in my equation, y is equal to -1/4, what was it here? X minus 6 times x plus 2. Instead of writing x, because I know that x value is already going to be +2, I can plug in a +2 and then solve for y. So I get -1/4, 2 minus 6, which is -4, and then 2 plus 2, which is +4. I get -1/4 times -16, so I get y is equal to +4. Oops, I'm running out of room here, which means my vertex occurs at 2, 4. That's where my vertex should happen at. The last thing I have here is my y-intercept, and that occurs when my x is equal to 0. And I know that from my previous, I know that a times r times s will give me my y-intercept. So I have -1/4 times 6 times -2. And when I multiply all that together, I should get +3. At this point in my life here, I'm going to start plotting the points that we have. Okay, labeling my axes with my y and my x. And the points that we're going to plot are all the points that we have. So we have the vertex, we have the x-intercepts, and we have the y-intercept. And then we could use the axis of symmetry to find any additional points. So 2, 4, 1, 2, 1, 2, 3, 4 will be there. Then we have x is equal to -2, and x is equal to +6. And then we have my y is equal to 3. For my y-intercept. My axis of symmetry goes right through my vertex here. It's an imaginary line, so we don't actually have to draw this in. But remember that if I have a point that's 2 away to the left of my axis of symmetry, I will have that identical point that's 2 away to the right of my axis of symmetry. So I will also have a point here. I could connect those dots with a nice curve, and that will give me my parabola, and I know that it's opening down because that is what I found out at the very beginning there. If I'm not too confident, or I just want to double check that I rock, because I know we all do here, we can go ahead and plug that in to Desmos to verify our questions or our answers here. X plus 2. And here we go. Vertex, same as what we got. Y-intercept, oh baby. And our x-intercept's the same as well. And again, if we used our axis of symmetry to figure out that we had the point at x is equal to 4 to be the same as my y-intercept. So if I plug in x is equal to 4, I also get that 0.43 that we added in. Beautiful. Last but not least, our domain and range. And now that we're all graphed out, we can totally get these done. Our domain is our lowest value of x to our highest value of x, which is -infinity to +infinity. And in set notation, it is the set of all x such that x is an element of the reals. And for our range, we have a maximum, which means our lowest value of y is negative infinity and goes all the way up to positive 4, and 4 is included, so that is a hard bracket that we are using. And in set notation, we have the set of all y such that y is less than or equal to positive 4, and y is an element of the reals. Alrighty, that is it for today's notes. There is some homework, which is just 2 questions for you to get done, which are very similar to our last 2 questions. Other than that, that is all for me today, and I will see you later for 7.4. Bye!